In this tutorial, you are going to learn how to code up a deep queue agent to beat the game of Pong. As a bonus, you're also going to learn how to use the OpenAI Gym Environment wrappers. Let's get started. So we start as usual with our imports. We're going to need a bunch of stuff from the Keras layers. We're going to want the activation function. We're going to want the dense layers, the conv2d, as well as flatten. All of these will go into making our models. We will also need the sequential. That is how we build models in Keras, and the load model function for loading saved models. If you have a slow GPU or you're training this on CPU, you're definitely going to want to use checkpointing so that way you can do it in your spare time. We use the atom optimizer, of course, and we want the back end as K. This gives us access to a bunch of functions from the Keras library, like the max and stuff like that. And of course, we're going to want NumPy to handle NumPy type stuff. So let's start with instantiating a class to handle our replay buffer. And the purpose of this is to keep track of the states, actions, rewards, new states, and terminal flags that the agent encounters as it plays the game so that they can sample them later. And this is pretty straightforward. There are a number of ways of implementing this. You can use something called a dequeue, which automatically handles appending stuff to the end and popping stuff off the other side as you go along. I don't particularly like that implementation. I'm just going to use a straight up NumPy array so we can pre-allocate all the memory at the very beginning. And of course, you want to keep track of your member variables. A mem counter will just keep track of the last stored memory. And of course, MP float 32. So our states are going to be screen images. So we're going to have to handle some pre-processing. We'll handle that at the very end in the wrapper functions for the OpenAI Gym's Atari library. And so all of these are going to be float 32 data types. And the new state memory is pretty much identical with respect to the shape. It just gets a different name. We also need an action memory, and that is just shape mem size. We use NumPy int 32. We don't really need 64-bit integers because we're only dealing with numbers from 0 to whatever 20 in the general case, and in Pong it's 0 to 5. So you don't need large numbers. So int 32, you could even get away with int 8 NumPy unsigned int 8, but whatever. Reward memory NumPy zeros. Type MP float 32. We need a dot there. And finally, a terminal memory. This handles saving the done flags. I'm going to start doing this a little bit differently. My previous implementation wasn't necessarily the best way to do it, so you'll see how I handle it here. Mem size equals MP uint 8 unsigned integer 8-bit. So it just means from 0 to 255, and really it's only going to be 0 or 1. So now let's handle the function to store a transition. It takes a state, action, reward, new state, and done flag as input. So the index is going to be the location of the last stored memory, which is where we want to store this memory. Self.mem counter modulus self.mem size. So that tells you, where you are in the array. Self.state memory subindex equals state. Elf.new state memory at index equals state underscore. Reward memory index equals reward. Action and self.terminal memory at index equals done. Self.mem counter plus equals 1. So if you have seen my other videos on deep queue learning, I will typically use 1 minus done. Here we're going to do it a little bit differently. The better way to do this is to just save it as done and use this as an actual mask. So that way you can set everywhere that the episode is done to 0, and that makes it a much cleaner implementation without the kind of convoluted logic of doing 1 minus done. And of course, you want to increment the memory counter, and we are not doing a 1-hot encoding for the action memory. So next up, we want to sample the buffer. This is just going to get the memories out of the memory, and that takes a batch size as input. And the first thing you want to know is what is the index of the maximum memory you have stored, so that way you aren't sampling a bunch of zeros. That wouldn't be particularly useful. So that is the minimum of self.mem counter and self.mem size. And batch is just going to be a numpy array of size from 0 up to max mem of size batch size. And very important, we want to set replace equal to false. What this does is it means that we are not going to sample the same memory twice. Replace is true by default. This is another tweak I'm making for a really large memory of, say, 1,000,000. The probability of sampling the same memory twice is 1 in 1,000,000, so not very high, but we're going to use a much smaller batch, smaller memory size, considering the fact that we are using a bunch of images instead of just arrays. So keep that in mind. So next up, you want to say states equals self.state memory sub batch. New states equals self.new state memory batch. Actions self.action memory sub batch. We don't need the double equal sign. Rewards self.reward memory batch dones terminal memory batch. And you want to return states, actions, rewards, new states, and dones. So that is it for handling the memory. So that is pretty straightforward. The next thing we need is a function to actually build our deep queue network using the Keras Framework. And we're not going to stick this in a class because it's not really necessary. It's just a single function and it doesn't handle any additional data. So it doesn't contain data, it's just a function. So that makes it a good candidate for just a function, not necessarily a class. So you want to pass in a learning rate, number of actions, input dims, and FC1 dims. So that's really the only hyperparameter, the FC1 dims. In the model, everything else is going to be dictated kind of just by decree here. So we'll say model equals sequential. This tells Keras that we're going to build a model out of a sequence of layers. So the first layer is going to be a conv 2D, that's capitalized. Filters equals 32, kernel size equals 8, strides equal 4, activation equals relu, and input shape equals star input dims, comma, and then another one of these. No, one of those. Sorry, there's a lot of commas here. Data format equals channels first. And then I need 2 parentheses to close it out. Correct. So what we're doing here is we're adding in a 2D convolutional layer with 32 filters, a kernel size of 8 that just dictates the size of the matrix that we slide over our image. It'll be 8 by 8, and we'll skip 4 spaces as we go along. What's important here is this data format of channels first. So if you don't set it, there's a config file hidden deep within your directory structure that dictates this because it varies between deep learning frameworks. I'm specifying channels first because of the way that I will be returning a batch of frames from the environment in the OpenAI Gym wrapper. So you must specify this, otherwise you're going to get some errors. Next, you want to add another convolutional layer, 64 filters, a kernel size of 4, strides of 2, activation equals relu, and you don't have to worry about the input shape here because it's inferred from the input. So you just have to specify the data format equals channels first. Next, the last layer, model.add, at least the last convolutional layer that is, filters equals 64, kernel size equals 3, strides equal 1, activation equals relu, no, comma, and data format equals channels first, 2 closing parentheses. Okay, so what this will do is it will take a batch, in this case, let's say a batch of 32 of stacked frames. So we have to stack the frames to give the agent a sense of motion. Like if I show you a single picture from the game of Pong, you won't know which way the paddle or the ball is moving, and so you can't really figure out how to play the game from a single image. So we have to pass in a sequence of images. Come on, kitty. We have to pass in a sequence of images, and in this case we're going to use 4. That's kind of the default, the standard that people use. In theory, you really only need 2. I haven't experimented with it. That is an additional model hyperparameter. I would encourage you to go ahead and play around with that. But this will take this batch of stacked 4 frames and convert it into a set of features for a dense neural network that will tell us the value of each action for that corresponding set of stacked frames. So next you want to add a flatten layer, and this will just take your input and flatten it because it comes out as a matrix, or rather a set of a whole set of matrices. Next you want to add in a dense layer, and that will output FC1 dims with a ReLU activation. And finally you want to add a dense layer that will take and actions as output with no activation. We just want to get the value of the action, so it's linear, which is default. So then you want to return the model. Very simple. This is our deep Q network. This will be both of our evaluation and target networks. Very, very straightforward. Next, let's make an agent class that derives from the base object. The agent is where we're going to store all of the goodies like the memory, the network's action choosing, and learning functionality. So the initializer takes quite a few parameters: a learning rate alpha, gamma. If you're not familiar with the gamma, is the discount factor. So you want to multiply the rewards from the resulting states by some discount factor because there is some uncertainty in those rewards, and you don't want to give them full weight. So typically something like 0.99. It's a model hyperparameter. You can play around with it, but people typically use 0.95 to 0.99. Epsilon, that controls the proportion of the time that the agent will select greedy or random actions. So the agent starts out without knowing anything about the environment and takes random actions to start understanding how its actions affect that environment, and then over time it decreases that random factor epsilon such that it eventually converges on a mostly greedy strategy, meaning that it picks the actions it thinks are best. You never want to leave it at 0 precisely because you never know if there's some better action out there. You always want to leave it something small but finite. Next we need a batch size, a replace parameter. Replace just tells us how often we're going to copy the weights from the evaluation to the target network. That'll be clear in a moment. Input dims from our environment. An epsilon decrement. I'll give it a default value 0.996. Actually, let's do, no, I take it back, 1e to the minus 5. We'll do that. Epsilon min, a default value of 0.01. That is the minimum value of epsilon. A mem size, 123. Set it to 1,000,000 by default. Doesn't really matter. We're going to pass in parameters in the main function anyway. We also need variables for the file names to save the model, because this does take quite a while to train. Equals q eval.h5 and q target fname equals q target.h5. So there is the initialize function. So the first thing we want is the action space, I for I in range, and actions. What that will do is tell us the set of all available actions. In the case of Pong, it is 0 through 5. And of course you want to save the relevant parameters. Epsilon decrement. We need batch size. That is for memory sampling, of course. We also need the replace parameter. And what else do we need? We need to say that we need to set self replace, otherwise we'll get an error. Self.q target model file equals q target f name. Q eval model file q eval f name. What else? We need a learn step. This will tell us how many times we have executed the learning function. That is important because we want to update the target network parameters every 1,000 steps or so. Next, we need a memory equals replay memory. Sorry, replay buffer. And that gets mem size and input dims as inputs. And we need 2 neural networks. QEval build DQN alpha n actions input dims and 512. This is kind of the default for the first fully connected layer, 512 neural network units. You can play around with that. That's another model hyperparameter, but I get pretty good results with just 512. Q next build DQN. It's the same deal. Actions input dims and 512. So that's effectively identical. It just doesn't get trained. We only update the model parameters. So next, let's handle that. Replace target network. Say if self.replace is not none, and let's see, self.learn step modulus self.replace equals 0. Self.q next dot set weights. This is a very straightforward way of copying weights. Self.q eval.get weights. Just a single line of Keras code. Very nice. You know what? Let's see if self.replace is, let's say, not equal to 0 rather than none. Not equal to 0, 0, and learn step modulus equals 0. Okay, so that will update it every 1,000 steps is what we're going to set it to. And we can even, now we won't set the default. Okay, next, store transition. So this is the interface between the agent and its memory. State, action, reward, new state, and done. Self.memory.store transition, state, action, reward, new state, and done. Very straightforward. So only a few functions left, at least in the agent class. Def choose action, self, and observation. So what this will do is help the agent decide what to do. Random.choice less than self.epsilon. So in other words, if it's less than epsilon, action equals np random choice self.action space. If the random number is greater than epsilon, then we want to take a maximizing or greedy action. So else state equals np array observation, and copy equals false, d type equals np float 32. So what we're doing here is from the environment we're receiving an observation, and by default the observation is a single image, but we're going to override the OpenAI Gym classes and turn the observation into a stack of 4 frames. And so it's a 3-dimensional matrix, and the convolutional neural network expects an input with 4 dimensions, so we have to basically add an extra dimension to it in order to preserve the ability to use it for both learning as well as choosing actions. We don't want to have to define 2 different functions for making predictions, so it's easiest just to add an access to the observation. Then you want to feed that state through qeval.predict state, and action equals np argmax actions. Finally, you want to return the action. Very, very straightforward. Next, we want to actually have the agent learn something. So this is going to be only a few lines of code. That's just really, really cool. So if self.memory.mem counter greater than self.batch size. So we only want to learn when we have filled up batch number of memories. We don't want to learn from zeros, and we don't want to learn from the same memory over and over and over. So only learn when you have filled up the memory to the size of the batch. And then when you have, you say state, action, reward, new state, and done equals self.memory.sample buffer self.batch size. Let's tab that over. Okay, so this will retrieve a batch of memories from our memory. Next thing you want to do is replace the target network if appropriate. Then you want to say we want to actually perform the feed forwards to get our I feel like I missed something up here in the model. I must have missed, I missed something up here. So that reminds me, so what I missed is model.compile optimizer equals atom, LR equals LR, and loss equals mean squared error. How could I possibly have forgotten that? Could it be because it's late at night? Okay, so if you're not familiar, what this will do is it will compile the entire model, give it an atom optimizer with learning rate specified by LR, and tell a mean squared error loss. So let's come back down here. So what are we going to calculate the mean squared error of? So in Q-learning, what the deep neural network is doing is it is being fed a set of states and trying to figure out the value of each action for that particular set of states. And up here in the choose action function, sometimes it picks one at random, and sometimes it says, hey, this set of states, I think the maximum action is this, and so I'll take that. And so what you want to do is you want to take the delta between the actions the agent actually took and the action that is maximal for the next set of states. And so we actually have to do a couple feed forwards to get a couple of different they come out as arrays basically. So we say q eval equals self.q eval.predict state. That gives us the value of the current states. Q next equals self.q next.predict new state. That tells us the values of the next states. If the next state is terminal, then its expected future reward is by default 0. So q next sub done equals 0.0, where done is a mask that tells us 0 if it's not done and 1 if it is. So it's just a handy dandy mask array effectively. And next we want to perform some array slicing. MPA range self.batch size, and we want to say that the q target, the value that we're shooting for, equals q eval as a copy. So if you're not familiar, if you just say q eval, it'll be a reference, so anything you do to q target happens to q eval. That's not particularly useful for us. So to get an actual copy, you have to do the the colon in brackets there. So q target is a copy of q evaluation, and you say q target sub indices. So for every member of our batch sub action, so the value of the action we actually took equals reward plus self.gamma times np max q next axis equals 1. So that is not proper formatting. Let me do this. So what this is doing is saying, okay, so the values for the actions we didn't take are just equal to q eval, and the values for the actions we did take are equal to the reward we received plus the discount factor times the maximum value of the next state. And the axis equals 1 just tells us that it's taking the max over the actions, whereas the zeroth axis is the states. So this tells us the reward plus gamma times the value, the maximum value of the next possible state. And then what you want to say is self.qeval.train on batch state and q target. So what this does then is it passes the sequence of states through the evaluation network and computes the outputs, and then takes the delta with the q target and does the mean squared error loss. And so you want the loss for the actions the agent didn't take to be 0. That's why we have this. And you want the loss for the actions the agent did take to be maximal when the agent did not select the maximal action for the next state. I hope that makes sense. So next up, that is the sum total of training the network. Very, very straightforward if you can follow that logic. So next we want to handle the epsilon decrement. Epsilon minus self dot epsilon dec if self dot epsilon greater than epsilon min, else I need a self there. self.epsilon min, else self.eps min. It's not epsi min, this isn't Pepsi here, this is eps min. And it's eps dec, if I remember correctly. So this just is a linear subtraction from the epsilon over time. You can do a multiplicative factor where you multiply by some number. You can do a square root kind of thing. You can do any, really you can do any type of decrement you want. Linear is the easiest, and it gets the job done, as you saw from the video at the beginning of the tutorial. Finally, you want to increment the learn step counter, so that way you know to update the target network at the appropriate time. Next, we want to define a function to save the models. This is very important because Keras in particular is quite slow. I have an implementation of this in PyTorch as well, and it is significantly faster. We're talking 20-30% faster. I haven't benchmarked it, but just watching it go by, it's significantly faster. So you're definitely going to want to save the models, and I'll upload some of my model weights here, so that way if you want to do a get pool, you can play around with it and test it around in evaluation mode yourself. qeval.save self.qeval model file self.q next save self q target model file, and I'm using target and next kind of interchangeably. You could be more strict in your terminology if you want. Print saving models and next def load models. You say self.qeval equals load model, self.qeval model file, q next d, no that won't work, load model, self q next, no target, I'm even getting confused, target model file, print loading models. Okay, so that is it for the DeepQ network file. About 125 lines of code gets the job done. Pretty straightforward. Next up, we have to handle something we haven't touched on this channel. So let's go over to utilities.py. So this is my plot learning function. I don't think I've ever showed it on video because it's just a plotting function, whatever. But next we have to do some black magic, some wizardry. So this is something I only recently came to learn. We need to actually override the gym environment with our own functions to handle frame stacking. So this is non-trivial, and I'm not going to explain it too well here. I'm saving that for a course, but I'm going to show you how it works so you can do a get pool and play with it. And I'll have to update all of my other code to use this as well in the interest of transparency, so that way it actually functions properly. The first thing we want to start with is a skip environment. What this will do is it'll handle skipping for us. So some of the environments by default will repeat your action n number of times, typically 4, and but a quarter of the time it will take a different action than the one you selected. So it's non-deterministic, it's stochastic. They do that so that way the episodes are non-deterministic. It makes perfect sense, but that's not what we want. We want to dictate precisely what happens in our particular set of experiments. So we are going to dictate how much we're going to skip and how much we're going to repeat. And then we're going to use an environment that does not do any of that stuff by default. It just does exactly what it is told. It's a good little soldier. So the initializer takes self, an environment, and a skip. We're going to use 4 by default. We're going to use super skip environment self.init environment and say self._skip equals skip. So next we want the step function, and this is precisely the env.step, so we're going to override that function right now. It takes self and an action as input, as you would expect. We're going to need a variable to keep track of the total reward. We will need a done flag, and we're going to say for blank in range self._skip, obs reward done and info equals self.env.step action. So this will call the step function from the base environment and execute it 4 times and get back 4 different observations, rewards, and stuff. So say t reward plus equals reward. And if done, then break. Because if you end the episode, you don't want to keep repeating the same action. It doesn't make any sense. After you've executed 4 times, you want to return the observation, the total reward received, the done flag, and the info. So notice this will only return the last observation. This could be some room for improvement. I don't know, but this works as you saw from the video. So I'm going to roll with it for now. So the next thing we need to know is how are we going to pre-process our frames? So not all of the frame, in other words, not all of the screen image includes useful information, like it has a score. The agent doesn't need to know the image of the score. Who cares? It only needs to see the paddles and the ball, really. That's all it needs to see. So we're going to crop the image and reshape it into something smaller, because by default it's 210 by 160 by 3 channels RGB. So 210 by 160 is kind of big. We're going to make it 80 by 80. We're going to make it square. Doesn't really seem to matter, because when you're playing the game, all of the frames go through this function. So all of the frames it sees get resized. It never sees a 210 by 160 by 3 frame. It only sees 80 by 80 by 4 by skip factor by stack size frames. So we want a class to handle the pre-processing of our frames, and this derives from Gym Observation Wrapper. Our initializer takes an environment as input, super preprocess frame self.init env, and we also have to handle the observation space. If you recall, the observation space is just basically the frame size. In this case, it's going to be a stack of 4 frames. We'll get to that in a minute. This doesn't handle the stacking just yet. That happens at the end. So you say self.observation space. This is from the OpenAI Gym library. If you look at their documentation, you'll see this. Gym.spaces.box, low equals 0, high equals 255, shape equals 80 by 80 by 1, and let's put that on the next line. Whatever, dtype equals mpuint 8. So we're going to recast, we're going to reshape the observation space, and we also have to redefine the observation function and self and observation as input. We're going to use some, what are these called? Decorator magic here. Return pre-process frame.process obs, a little bit of voodoo there, at static method def process frame. And the reason we're using a static method is because we're not accessing any data from the class. We're just acting on data passed into it. So we say new frame equals numpy reshape frame.shape as type mp float 32. New frame. So we are passed in with an image with 3 channels RGB, but the neural network doesn't really care about red, green, and blue, so we're going to make it grayscale. And you do that by doing some multiplication of the R, G, and B elements from your matrix. And I just looked this up on Stack Overflow. This isn't something I derived or anything. 0.299 times new frame, all rows, all columns, the 0th channel, plus 0.587 times new frame 1 plus 0.114 times new frame 2. New frame equals, here we're going to handle cropping. So I did this by experimentation. 35 to 195, skip 2, and then take the rows and skip 2 dot reshape 80 by 80 by 1. So it'll have 80 by 80 pixels and 1 channel because it is grayscale, no longer RGB. New frame.as type mp uint 8. Next, we have to handle so this handles all the processing, but notice the channels are last. If you come back to our function down here, we specify channels first. That's a problem. So let's define a class to handle that problem. So class move image channel. And I guess you didn't necessarily have to do it this way. I'm doing it this way because I'm trying to keep some consistency with my PyTorch implementation as well. I don't like having, aside from the models, I don't like having framework dependent code, so I'm just doing it this way to keep things nice and consistent. So move image channel gym dot observation wrapper def init self environment super move image channel env and self.observation space. So since we're moving the channel, we have to redefine the observation space. Gym.spaces.box low equals 0.0, high equals 1.0, shape equals a big mess. Self.observation space.shape -1, batch dimension self.observation space.shape 0, comma observation space.shape 1, and then 1 comma, and then d type equals np float 32. Next, def observation. I feel like there's one too many indents here. Yep, def observation, self observation, and this will handle the moving of the axis, move axis, observation to 0. And again, this did one too many indents. Okay, so now we have to handle a scale frame, because we're going to divide by 255, so that way we're scaling the inputs to our convolutional neural network. Gym observation wrapper. Sorry, it's a class. And say def observation. We don't need a constructor for this. Self obs. And return mp.array obs.astype mp float 32 342 divided by 255.0. Save so I don't lose anything, and say we have one final class to handle here, and this is where we're going to actually buffer and handle these frame stacking. So we're going to call this a buffer wrapper, and again that derives from gym observation wrapper, and we'll say def init def init self env and steps. So we're going to want to dictate how many steps we repeat the frame for. Super buffer wrapper self dot init env self dot observation. Now since we're stacking, we also again have to change the observation space. Gym dot spaces dot box env dot observation underscore space dot low dot repeat and steps axis equals 0. So this will just repeat the low end 4 times, and say env dot observation space dot high dot repeat, and steps axis equals 0. And finally the d type equals mp float 32. No, there. Okay, now def reset. This handles the environment reset self. So we're going to define a buffer mp zeros like self dot observation space low mp float 32, and say return self dot observation self dot env dot reset. Finally, def observation self observation. Now is where we stack the frames. We say self dot buffer -1 equals self dot buffer 1 onward. So this will pop off the leftmost or the earliest frame, buffer -1, and then append the most recent frame to the end, self dot buffer. Finally, we need a function to glue all of this together. Def make environment, and that takes an environment name as input. Env gym.make env name. So this will call the base environment, in this case Pong no frame skip v4, and then say env equals skip environment. So then what we will do is we'll add in the frame skipping, so it'll repeat the action 4 times, and then we're going to say preprocess frame environment. So this will add the frame preprocessing, and then we want to move the channels, image channel env, and finally env equals buffer wrapper environment and 4, and you want to return a scaled frame env. Scale frame, yeah, not scaled. Okay. Woo! Okay, so that is done. Pretty straightforward. Now we are ready to head to our main program and glue all this together, test it out, and see how well it works. So let's come over here, and first thing we want to do is we want to import numpy's np from dqn Keras, import the agent from utils, import plot learning, and make environment. If name equals main, then env equals make environment, and we're going to pass in Pong no frame skip v4. So this will invoke a deterministic environment, which is the no frame skip, meaning the base environment itself doesn't do any frame skipping, and it does the exact action you tell it, and then it'll do all of the magic here. So it'll make it first, and then it'll apply all of these classes. It'll override the base methods from the base class. Basic inheritance stuff. If it confuses you, then put in some print statements in each of the functions here. So in, say, the observation functions and the process frame and the step and the stuff like that. So if you get confused, go ahead and add a bunch of print statements in to kind of get some clarity in your mind around what is the order of operations with respect to the observation, manipulation, and reset functions. Next up, we want to say num games. It doesn't matter, I'm not going to let it finish, but something like 250. I found it gets pretty good results in 250 games. We need a variable to keep track of whether or not we want the loaded checkpoint. We're going to start out as false because we're training, but when you want to run an evaluation mode, this would be true. We're going to want a variable to keep track of the best score, and that is for saving our models that perform the best as they go along. It starts out at -21 because that's the worst score it can get. So if it's better than the worst, then you start saving. So we need to instantiate our agent. Gamma of 0.99, epsilon to start out of 1. Now if you want to do if you want to load a checkpoint and do evaluation, epsilon should be equal to epsilon min. A learning rate of 1 by 10 to the -4. Input dims equal 4 by 80 by 80. Why is that? Well, we're stacking 4 frames, and each one of them has been pre-processed into the shape of 80 by 80. Next, we need the n actions. So for this environment, it's 6. Memory size of 25,000. Epsilon min of 0.02. So 2% of the time, it will always take random actions after epsilon is decayed to this value. A batch size of 32. Replace of 1,000. So every 1,000 moves, it'll take the weights from the evaluation network and copy it over to the next network. And epsilon decrement equals 1e minus 5, not 56. So that will decrement epsilon by 1 part in 100,000 every single step, every 4 steps. Sorry. If load checkpoint agent.load models. So we need a file name to save our learning plot. I didn't let it finish. It takes a long time in Keras. Pong no frame skip v4.png. But by all means, go ahead and try it on your own. Scores, epsilon history, empty lists, and steps equals 0. This is just to keep track of the number of steps that the environment has taken over time. What I call num games. Say score equals 0. observation equals env.reset, and what will this do is it will come over to this and call all of these various reset functions. Where is it? The only time we've overridden it is here, and so what that will do is it'll get the initial observation and replicate it 4 times in our buffer. Very, very handy. Say done equals false, while not done. Action equals agent.choose action observation, so it takes in the stack of 4 observations as input, and we want to say observation underscore reward done info equals env step action. So this will of course call the env step function here, so it'll execute that action 4 times and return the last frame and stack it. Sorry, wrong file. env.step action. Then we say n steps plus equals 1, score plus equals reward. If not, load checkpoint. So if we're not, if we're training, then we want to say agent.store transition observation action reward observation underscore and done. And once you've stored the memory, go ahead and call the learn function. If you're not learning, then why not render the environment? Nice and handy. Finally, observation. I always have difficulty typing that. Observation equals observation underscore. And at the end of the episode, scores.append score. So every game you want to say, okay, what is the average? Average score equals np.mean scores minus 100 on. And you want to do this so that you have some idea of whether or not your agent is learning. So as it's in the very beginning, the epsilon is quite high, so it's taking mostly random actions, so you see the average score fluctuate around something really bad. But then as epsilon starts to approach around 0.5, in other words 50% of the time it's taking greedy actions, the mean score will start to really improve quite dramatically over time. So then print episode I score average score %.2f average score epsilon 2f agent.epsilon steps and n steps. That's what I called it. So if average score is greater than best score, then you want to agent.save models, and this gets kind of ugly. I'm going to leave out the print statement. Well, no, fine, whatever. Print average score %.2f better than best score 2f, and then %average score best score. So all this will do is print out the fact that we're saving the model because the average score is better than the best score, and then of course you want to save the new best score. And at the end of the episode you want to append the agent's epsilon, so that way when you do your learning plot you can see how the score improves as a function of decreasing epsilon. And finally at the end of all of it you want to do the plot learning I+1 for I in range len of scores. Actually I changed that for range num games, and then plot learning x scores, eps history, and file name. Okay, so that is all of it. So we've covered an enormous amount of ground. The only thing that remains is to go to the terminal and see how many typos I made. So here you can see the model I currently have running. It's getting a score of 16, 16, 19, best score, best average score of 17 point something, and of course it oscillates around over time. But let's go ahead and see how the code we just coded up does. So Python main Pong, yeah, that's the one. And then my stupid my install is borked, so let's see. So it gives me a bunch of warnings. So let's see. Name gym is not defined. Okay, that's easy. Let's say nano utils.py. import gym. Whoop, wrong button. Control X, not Control K. One more time. So it looks like it's unhappy because I'm currently running a model. You know what? All right, let's kill that and do it again. The things I do for you guys. So, okay, name observation is not defined. Okay, so let's check it out. That is in line 95. MP move axis. Okay, so I know where that is. That is down here. That is in the move image channels, self, obs, because I misspelled it, observation. Try it again. Name choice takes at least one positional argument, 0. That's because that is the DQN Keras file. That's in line 84 down here. Oh, good grief. Where is it? It says if MP random choice greater. Okay, that's in the choose action function. Sorry about that. There's no lines in here. I had to change my file. MP random, not choice, random.random. Skip environment object has no attribute skip. Why not? Let's scroll down. Self dot underscore skip. Range self dot underscore skip. That's right there in the constructor. Self dot underscore skip equals skip. Range self dot underscore skip. That is in line. Interesting. Very interesting. What have I done? That's why. Okay. All right. Wow. As usual. Alrighty, so now it is running. Let's make sure it gets through at least one iteration of the learn function without erroring out. Okay, looks like I can even save models. Perfect. So as you saw from the other tab here, it does quite well over time. Within, a few hundred episodes, it is quite good at the game. And I generated the output at the beginning of the game using something similar. So yeah, within a few hundred games, it has already effectively beaten the environment. It can get an almost perfect score. I think it got a score of 20 instead of like a delta of 19. So it was 21-2 basically. So quite good performance. And you can even see here, it got a score of 21. So a perfect game. And it's probably not the only one if you scroll up. Yeah, right here's another perfect game, another perfect game. So it can get perfect games. I am going to upload the model parameters to the GitHub as well as all of this code so you guys can go ahead and play around with it. Some things to consider is that this would need to be modified to handle other environments because I have done a very specific type of cropping for the image. So that's something to modify if you do a fork. But otherwise, this is a fully functional implementation of Pong in Keras using DeepQ Learning. I hope this was helpful. Please share this video if you found it to be so. Leave a comment down below, subscribe, and hit the bell icon. I know only 14% of you, according to my data, are getting my notifications. Make sure to leave a comment, and I will see you in the next video.